So my name is Armin. I work for a company called Sentry, and we are a crash reporting company. And this is going to be our experience in building something for NDK. Our NDK was a bit of a rabbit hole experience because we are not really from an Android background, and a lot of what we built we thought would be a little bit easier. So this is really our experience in actually doing a crash reporting framework for NDK. So we have handled a lot of platforms for crash reporting already. In particular, we have done C and C++, but we haven't done it on Android. So this is sort of new that we do it on Android. And we want to go a little bit about why that's kind of tricky and what some interesting learnings from this are. So who are we? It's a little bit of a joke, but we're kind of a stack trace company, so a lot of what we do is stack traces. We can tell you why your app is misbehaving, and primarily we do this because when your app crashes, we show you a stack trace. So this is what a stack trace looks like. What's interesting here, and this is a little bit relevant to the talk, is that we want to show you a file name. We want to show you a line number. We want to show you the function name. And if we can accomplish it, we want to show you the source code that goes around it. So this is sort of what the end result is supposed to be. As we mentioned, we already had that, just not for NDK. So my name is Armin, and my background is actually Python more than it is anything else. I love Rust. We do a lot of Rust at Sentry. But not really Android, right? So I work in Vienna for the client infra team. And there we are responsible for writing SDKs for Sentry as well as the event processing. So when the SDK sends some stuff in, there's a lot of stuff that works on the server. That's also under responsibility.
Hi, my name is Bruno Garcia. I'm a software engineer in Sentry in the same team, client infra team, and I have a background in .NET. So we're part of the client infra, which is based in Vienna, and over there we have to touch all sorts of programming languages, right? So although my background is .NET, I was exposed to Android and Kotlin, and this time NDK. So why are we here to talk to you about NDK? Like, considering you probably know more about Android than we do, there's one thing that we know pretty well, it's crash reporting, right? We're a crash reporting company. A lot of what we do is touches all different platforms. So we wanted to do something we're good at in C, C++, Java, and Kotlin, also for Android. So Android developers would be able to have good quality stack traces, also for NDK. So let's talk about why is NDK special.
So on NDK, you have basically a whole bunch of stuff that looks a little bit like Linux, but is not necessarily. So NDK gives a developer the ability to run C, C++, and a bunch of other compiled languages on an Android system. Even though like Android itself runs on top something that more or less resembles a JVM. And a lot of NDK code actually interacts with the Java code through a system called JNI, the Java Native Interface. And so that allows you to call from C or C++ or some other language that compiles natively down into basically the sort of the Java ecosystem and the other way around. But as far as the interactions actually go, it looks very much like its own operating system in that sense, because the paradigms that you have are very different. So on the base layer of what NDK actually does, there's an implementation of libc that's very Google specific. It's called Bionic, and it's not entirely like a normal libc implementation would be. So it misses a bunch of things that we would really like to have that's just not there, because Bionic covers a whole lot of what a lot of people need from a JVM, from a libc, but not necessarily everything that you need. And NDK also comes with a bunch of handpicked libraries like zlib. But it doesn't come necessarily with some of the other libraries that you would expect. So for instance, I would love to have a libuUID on there. It doesn't exist. There is no libunwind, which is for us very disappointing. So there's a lot of stuff that's missing in NDK that, since we already had a lot of code that runs on Linux, was expecting to be there, but really wasn't. So as we mentioned, we already did Java, right? And we also already had an Android library, and we already did C++. But just NDK wasn't really working. So our goal, as mentioned, is production crash reporting. And production crash reporting means that you have a stack trace in a release build and not just in a debug build. So everybody knows that you can get a lot of useful information out of a debug build, but the moment you go into a release environment, some other constraints come in. So in particular, production crash reporting or release crash reporting is fighting a few paradigms. The idea is that there is a debug build that gives you a lot of debug information, and there's a separate release build that just doesn't have a lot of that. And that's not really true, especially not on mobile, because when you ship, if you ship an application to a customer, it's very likely that their problem will only occur on a customer's device and not actually on your development environment. So you really want to be able to capture debug quality stack traces on a production build. So we need a whole bunch of stuff to support that. But there are some constraints that make it hard to do this in a release environment. Debuggability and performance are often at odds. So the lower level the language, the harder it is often to get some of the performance benefits that a lower level language has, and that's why you kind of write a lot of code in a lower level language, but you lose the debuggability. So in particular, stack traces and all that sort of debug functionality is often unavailable in C++. So if you, for instance, throw a C++ exception, the stack trace is typically not even captured. So you would have to find the facility to capture the stack trace with throwing the exception. And so this is one of the core problems that that code like a crash reporting library is fighting, is that what you have in a release environment is very different from what you have in a production, what you have in a debug environment. And to understand a little bit the context of this talk, we don't really care about the debug builds. All that matters for us is the release build. So we want to get stack traces only running on the release build. The debug build would also be nice, but it's not really something that we care about. So let's talk a little bit about what production builds look like on Android. So you have two runtimes to work with. One of which is the Java runtime, or it's actually more appropriately the Android runtime. And that's responsible for running Java code, Kotlin code, a bunch of stuff like that. And then you have sort of the C runtime, which a lot of people say is not even a runtime, it's just a bunch of low-level support stuff like memory allocations. And the C runtime is sort of the minimum set of stuff that you need to run any code at all. So it gives you stuff like memory allocations. But it also, in normal cases, gives you the ability, for instance, to do what's called stack unwinding. And that's the part that's actually surprisingly a little bit absent on Android. And we'll go into this a little bit. So the Java runtime more or less gives you the ability to run Java code. On Android, it's a little bit more complicated because it's actually not the JVM that runs there. It's on most modern Android phones is the Android runtime. But it sort of resembles what the JVM does. And in particular, it gives you a function that gives you a stack trace, which is pretty powerful. If you have an exception object, there will already be a stack trace on it. You can do something really useful with that. On a C runtime, it's very different. It's very low level. And it doesn't have anything there really to give you a stack trace. And even if you manage to get a stack trace, the only thing that you get is just some numbers, the instruction addresses, where the function would return to. And unfortunately, on Android in particular, there's actually no built-in support to get the stack trace. So you need to write your own, you need to bring your own stack unwinder with the application to get this facility. There are some theoretical ones which are available, but they are not really that good. So yeah, we care about stack traces. Readable stack traces on Java are not that hard, but if you use obfuscation tools like Prograd or R8, they will not be readable. They will not tell you where the function actually was. It will be whatever was obfuscated. So there's some stuff that's necessary on the server side where the crash report is being sent to actually map it back to what you expect. With C, it's a lot more complicated because the stack trace, even if you get it, is just a bunch of numbers. But we'll go into a little bit why on NDK it's particularly hard to get a stack trace. To get the numbers on the C side into function names, line numbers, file names, and so forth, you need what's called dwarf debug information. And dwarf debug information can get huge. And you definitely don't want to ship it with your app. It's way too big. So we get this debug info onto our server side where we do the processing. But there will be a whole separate section in this talk that actually goes into why this debug information is so hard to work with. So our goal is turning the funny numbers or human unreadable function names into something that we can work with and that users can comprehend. So let's start with Java.
So yeah, as Armin already mentioned a little bit, in Java it's easy, right? So throwable has a method get stack trace, and you have already an object. You can query the class name, package name, and line number. It's all good, except all we care is production. And in production, you're not gonna get the real names. You will minify your application for sure. You're gonna use something like ProGuard or R8, so your production build is like faster and smaller. But also means that when you call get stack trace, you're gonna get gibberish out of it, right? So during your release build, ProGuard outputs something like this ProGuard mapping file. So on the right-hand side, you have the code you wrote in Java in this case, for example, or Kotlin. And on the left-hand side is what ProGuard would rewrite your code to look like. So here's a simple example. It's just mapping from one thing to the other. It can get a lot more complicated with line number optimization and functioning lining. And this can cause some problems, right? Like if you use Java with reflection and use ProGuard, you already know that you have to create some rules. And with that means that you have to prevent minification from happening altogether. So that would break in runtime, even worse. So here we have an example of a ProGuard rule. It just says, hey, don't touch my exception types. Maybe you access them via reflection. But more importantly, and related to this talk, is if you do have a JNI bridge, if you're calling from C++ code in Java, you definitely don't want ProGuard to touch that, because again, it would fail at runtime, just like if it was in reflection.
So how do we get readable stack traces in C? It's much trickier. And the reason for that is that we need to do what's called stack unwinding. So this is to explain a little bit sort of the workflow that you would sort of expect. The application crashes, right? And so the first thing you want to do is get a stack trace. And we're going to go into like different ways in which you can do this on NDK. But what's most important, in order to get a stack trace, you need what's called unwind information. And unwind information is necessary because the way the compiler optimizes your code means that depending on how the compiler wrote the code, was actually necessary to go from the current instruction to the previous one, or more accurately to the one that it would actually return to, can be very complex. So we need this unwind info to unwind. The next step after you already have a stack trace is the stack trace at this point is just a bunch of numbers. And we need to symbolicate it. And symbolicate means we're going to take a number and a bunch of other information that's necessary to turn it into a human readable string. And we're going to use that debug information to turn it into function names and locations in files. And at the end, you can just render it, store it, whatever you want to do with it. And this is something that doesn't just apply for debug tools that make stack traces and crash reports. It also, for instance, applies to if you do performance profiling. Because a very common thing that you do when you performance profile something is you want to sample how many times you end up somewhere in a stack trace. So I don't know if you're familiar with dtrace, but the way these tools work is that they every n milliseconds take a snapshot of your stack, and they will say like, oh, we have been in this function, we've been in this function, we've been in this function. And so based on which branches you take, you can see like, oh, I'm always spending time in like this very slow function. So this is really important information. And depending on where you want to draw this line, you can run some of it more on the server or some of it more on the device. So we built a tool which is open source, which is called Symbolicator, and it can make a stack trace out of what we call memory dumps on the server side, or it can also just symbolicate individual memory addresses. So if you know I'm in function X and you want to know like what is that, you can just throw it into this tool. It's going to symbolicate it for it. This tool is also used in the back behind the scenes on Sentry. So as we mentioned, there are different ways you can decide do it more on the server or do it more on the client. If you want to do it on the server, what you would do is you would dump out the stack memory. So you would say like this thread has this much memory for stack. You take this, throw it into what's called a mini dump, and you can do the processing on the server. So there will be a little bit of stack data in it, which is maybe irrelevant. But dumping out stack memory is a comparatively easy thing. All you need to know is, where is my stack, how large is it, and dump it into a file. If I don't want to dump the memory stack, I could also do what's called a stack walking on a device. And then I get out individual addresses, and I can store it in the symbolic header. So how do I decide which one I want? Do I want to stack walk on the device, or do I want to do the memory dump? And as we mentioned earlier, we need the unwind info to do the actual unwinding. And so where's the unwind info? So the unwind info is typically stored in the executables. So it can be in a shared library that you load, or it can be in the code that you compiled. And this unwind info fulfills the purpose primarily for C++ to be able to invoke the right destructors if you throw exceptions. So if you throw an exception and it bubbles out a bunch of stack frames, it needs to deallocate the memory, or it needs to clean up some resources on the way out the stack. So this information needs to be compiled into the binary most of the time. This is what a stack looks like. So you have, you start at the top. Somewhere there is your data, some local variables. And then underneath that, so growing down to a lower memory address, you have more and more functions that you've been calling on top. And in the stack memory, somewhere there's an interesting part in it which is called the return address. And this is where it wants to return to. So if the function returns, it wants to jump there. But how do you get to that data, right? So the unwind information is what ultimately tells the stack unwinder where to return to. So you need to know what's the current address. You need to know the register state of everything else. And then you can take that information to pop one frame off to what was the previous one. And since, as we mentioned earlier, on production builds, you care about performance more than anything else, there can be a lot of optimizations applied. So in let's say like a long time ago, there was always a register which would point back to the previous frame, which was the frame register. But since we're short on registers, a very common optimization the compiler would do is it would just omit this frame pointer register. And so once this register is omitted, you need this unwind info because there's no heuristic you could fall back to, which is reliable. So as we mentioned, we need this unwind info, right? And this is sort of what the workflow typically looks like for people that use NDK or any other C++ workflow. So you start with your source code, you compile it. And from there, it sort of takes a branch. The executable makes its way into the application, on your device. So the executable gets distributed, and it crashes on the customer side. But with compiling that executable, you typically also get debug info out. So on Windows, that would be in a PDB file. On Mac, that would be a dwarf file. Same really on Android, because it's a Linux system, there you also get dwarf data out. And this debug file typically gets split off, and you can retain it, and you can do some stuff with it. And in this case, you can upload it to Sentry, and we could do some stuff with it. The problem with that is if you only give us the debug data, there's some crucial information missing, which is the unwind information. Because the unwind information is only contained in the executable. So if you were to stack unwind out of memory dumps on the Sentry server side, you would also have to give us the executable, because otherwise we can't do it. So this is sort of the workflow that you use with a system like Sentry. But even if you want to debug it yourself, so for instance, if you have a crash on an Android device, you get actually a stack trace dump to a log, and you can throw this in a tool like NDK crash or an NDK stack, which would parse this, and it also needs both these informations to do anything useful. Or if you want to throw it into a local debugger like GDB, you also need both things. So let's just say we would like to unwind out of memory dumps. For a lot of people, that's sort of the ideal case. I will go into detail of why you want that. But that would be great. The problem with that is that really only works on iOS. And this is the mode in which we went into with an expectation, because on iOS, the total amount of devices you will ever observe is very limited. There's a fixed number of iPhones, there's a fixed number of iOS releases. You can, or we can, just get all the data, store it on our site, and then identify it. So the total amount of observable things is very limited. On Android, that's a little bit different.
And Android is much harder. And it's harder because the ecosystem is fragmented. Like Android being open source, you can pull the code, create your custom build. All these different vendors create their own, like Samsung will have their own builds and their own phones. And this makes much harder for us to collect symbols, right? So this is not a problem that affects only a company like us doing crash reporting, but anyone who wants to debug crashes in someone else's phone, like in the clients. So what Facebook decided to do is they decided to upload system images from their apps. Like, so if you have an Android device in your pocket with a with a Facebook app, this is happening in the background for you. So we could do something like that, although we don't have an app as popular as Facebook to do that without your consent. So we have to also consider a different option of what else can we do if we can't do that. So one thing we can do is we can stack walk on the device. That comes with a few constraints that Armin was already mentioning.
So how do we stack walk on a device? We need a stack walker. So we can stack walk on a device conceptually because the unwent information is on there. This is the part where NDK gets really confusing because we all know that Android can stack walk. It has to. And if it crashes on your device, you can actually get a stack out of it. So it's technically able to do that. In the Android source tree, there's a whole bunch of stuff in there that can stack walk. There's libcorkscrew, which stopped being maintained many years ago and only supports 32-bit ARM CPUs. There's libunwind, which is an open source stack unwinder, which is very popular. There are some patches on it that Google wrote. Google itself actually stopped using libunwind a while back. It instead uses libstackunwind, which is a Google custom, also somewhat open source. It's an open source version of a stack unwinder. It's written in C++. It's huge in comparison to everything else. And this is sort of the only one that's actively being maintained for Android. And it's the one that Google itself uses. The downside of this is that it's actually not being exposed to you as a customer. So to understand how to even get that going, and a bunch of people have been doing that, there are open source forks of that, where someone took the stack unwinder from the Android source tree, copied it into a GitHub repository, made it work to compile against the actual current version of NDK, took out a bunch of stuff that's unrelated. But it's these open source sort of versions of that which were dragged out of the source tree are kind of unmaintained. So they're much older than the most recent commits are that Google has on their side. Since it's written in C++ and since there's a lot of complexity going on, it requires a very large, what's called a SIG alt stack to actually do unwinding. So if you crash, the operating system gives you a separate stack to do some stuff in your signal handler. And this comes out of the box as a very small stack. And if you want to do stack unwinding in the signal handler with libunwind stack, you need to enlarge this. Otherwise, it's not going to work at all. And since the general version that you can get on the internet for open source use compared to the one that Google has have deviated so much, it's in a pretty disappointing state at the moment. So we would really like to have a stack walker that's exposed from Google. It's available on all the other platforms, but it's not there. So the second thing we need is once we have a stack trace, we need to figure out how do we get the function names from it, right? How do we get the addresses? How do we get the line numbers? And this information is in the debug information file. So we need to match them up with the executables on your device. And the way you do this, or the way ideally you do this, is you grab what's called the build IDs from that. So the build IDs are unique identifiers that match exactly the binary with the debug info. This information is thankfully contained in what's called the ELF header. You can use the DL iterate PHDR function to iterate over all the loaded ELF files. And if you know where in the memory to poke around, you can read it from there. One of the problems with that is that all the NDK versions are actually not having that function. Reason being that Google has their own C library, their Bionic one, which just didn't implement this part. So an alternative, and that's also what Google does internally, they are parsing the proc maps. So when the kernel gives a process memory, it has to establish a memory mapping somewhere. So each process has its own memory mapping, and the kernel provides a special file in proc pit map where you can see that. So this is an example from what this memory mapping looks like. So it gives you a memory range from where the mapping starts, where it ends, what the executable bits are. So it can be executable, it can be read, it can be write. There are a bunch of other flags that can be set on it. And it can map to a file. So in this case, you can see that this is the proc map for the cat command. That's what I used as an example. And you can see like from memory address 0x4, whatever, up to some relatively large number, this is where the executable is. And then there are a bunch of libraries linked into it. Like for instance, we can see that libc is linked in, and it appears somewhere in memory. The reason there's so many mappings per each one of those files is because some of these are sections that are read-only. So for instance, global variables are typically loaded into space somewhere. They might actually be right in that case. The executable itself is the only one that has the executable bit because you don't want accidentally to be able to execute stack memory. So you can see that a whole bunch of these things are mapped in different areas. And so if you have ever used Google's breakbat will actually on Android read this file because they already knew they didn't have a different API to work with. So that's one workaround that you can use on NDK to actually get to these mappings if you can't use DL iterate PHDR. But here's the problem with stack walking on device. And that's basically that the way this would work is that you're in a segfault, right? So basically, there are two ways in which it can go. One of them is typically a segfault. So you touch some memory you're really not supposed to touch, and the operating system punishes you for it and wants to tear you down. Shortly before it does that, it emits a signal called the SIGSEG, and you can intercept that. For that, it will invoke a signal handler. And signal handlers are very painful on POSIX, and they have all kinds of restrictions. The second option that you will typically find is that you have a recursive function that calls itself and eventually runs out of stack memory. So it runs through the top of the stack, and it touches some memory it's not supposed to touch. Now, the problem with that is if you run out of stack memory, you basically, the signal handler would run somewhere where there's no stack space anymore. So it can't run realistically. So the way Linux, and particularly Android, solves that is what's called a SIG alt stack. So a SIG alt stack is a separately prepared memory stack somewhere where your signal handler will run. So you can imagine this like you run out of stack space, the operating system says like, you can't do that, but let me, before I abort you, call your signal handler so they can do something. And that signal handler will run in the SIG alt stack. That is very small. It's so small that you typically can't do stack unwinding. The second problem with that is that even if you can do stack unwinding because you made it larger, is a concept called an async safety. So the signal handler gets invoked at the point wherever that thread was at the time. So you could imagine maybe it tried to allocate some memory, and that failed. And for whatever reason, while you're in this memory allocation routine, which typically has to be thread safe, thus will be locked, you're now in the signal handler. If you try to allocate more memory, you're going to deadlock because you're trying to fetch the lock that you were just failing on. So this concept is trying to called async safety. And if you look into all the functions you're allowed to call in a signal handler, it's a tiny set of observable functions. And in particular, most stack unwinders are not supposed to be called in that. So you're about to crash, you're about to do a whole bunch of stuff which you're really not supposed to do. So in the ideal case, we wouldn't do that. The first part we can solve because we can just allocate more stack space for the SIG alt stack, tell it, now please use that. So we would do that on startup, so we can give it 65K instead of 8K, which is more for stack walking. And then every future signal evoked from this point will have a larger stack space to work with. The second problem, however, is a bigger one. How do we prevent stack walking on a device at all? Because if we have async safety as a requirement, we're really very limited in what we can do. So if we don't have the ability to effectively allocate memory, we can write our own memory allocator, right? If there's a whole bunch of other stuff that we would have to do, maybe you can work around some of them. But at one point, you're out of options, and it would be easier for us to just dump the stack memory and then do everything on the server.
Yeah, and for that, we need a symbol server. So the thing that Facebook was doing under the hood, they're building a symbol server, right? It's something that their symbolication service can query to get the symbols that they need to symbolicate. Ideally, independent hardware providers would do that. So Samsung would provide their symbol server, and so would Google for the Android bits and so forth. Something that we plan to do is to actually collect symbols ourselves, like maybe we can go on device farms in the clouds to run tests in an app, and it's an app that only collects these symbols. And this should be good enough to allow us to build our own symbol server. So how do we put all this SDK together, right, with the stack walking on the client? First, on the NDK side, what we do is we hook to the signal handlers. We hook to the signal handlers. We also have to load the loaded images, so we know what was loaded in the process. And lastly, we will, like when the signal handlers trigger, we do the stack unwinding and we dump to disk. So with the event on disk, either if the app restarts or still if the app is still running before it crashes, the Java layer can detect that a file was written. It loads this file up. It can add more context, for example, things the user was doing right before the application crashed. And then it can open a connection to Sentry in the backend and send this event to Sentry. It's on the server side then we're able, like having the stack trace, there'll be just numbers at that point. We can look at symbols, debug symbols, and convert them into something you can read and understand. So your function names and line numbers, etc. We can also, in the case of Java, also do the ProGuard mapping, so it's all done on the back end. Finally, we just store it so that on the UI it can render and show you a nice view of what happened when the application crashed. This brings us to the last part. So when we had to put all this together, we want to allow you as a developer to use it. You add our SDK, we ship it to you. We want, it's easy enough for you to call all the Java code. It's immediately available for you to call. But to call the C and C++ code from your C code, it just doesn't work out of the box. And this is just not something that, it's a lack of support from the tool, like the tooling Android Gradle plugin and all this stuff. So when we build our NDK support, this is what comes out. Like all the ABIs that we support, we have the different native libraries there. And when you add this to your app, Android Studio can't see our libraries automatically. There are no header files there for you to refer to, and you're not possible to link against these things. So apparently the suggested solution so far is for us to build a Gradle plugin that will copy the native libraries that we bundled in our AAR into your app, and only then you can change your CMake list and link against it, and then call from your C++ code into our C++ code. It will, you don't need any of this to capture the stack, to capture crashes from C++. But if you want to call our code to do different things, then you will have to do this ugly dance here that we have.
So how could this be better, right? So we, as we mentioned earlier, we have some experience on other platforms, and we went into this project with some sort of expectations about how it would be. But then it turned out to be just very different. The amount of extra code that Android actually required, it was unexpectedly large. So if we could have some wish list for Center to bring us better things, it would be awesome if Android could include a stack walker. Every C++ platform we've worked with so far has one. Android really doesn't, because I guess Google doesn't consider that to be something that you want to a production device. The second thing is that the Bionic library just lacks a whole bunch of stuff. One of the things most C libraries have, and is actually required by POSIX to some degree, is what's called the getContext function and the uContextT struct, which lets you, if you call it, it grabs all the register contents and you can see what was there at that point in time. You can't write that function in C. You have to write it in assembly. And it's just not there on Android. So you would have to write some custom assembly code to get that. The lib stack unwind unwinder that Google has actually runs into this issue. And so they have some custom assembly code to read just the most necessary registers, like the instruction pointer register and the frame base pointer. But you can't get any all the other ones with built-in, with stuff that's sort of available. If you actually do manage to compile all of this in, there's no way to distribute it, right? You need to do some custom code to get your native libraries out of an AAR. There's no support for headers. So that would be really nice to have. It doesn't really seem like C and C++ is sort of the primary focus on Android. And it would just be nice if the tooling supports that out of the box. It's not too uncommon that you want a C companion library that's also available to other things. It would be very nice if you could just download stuff from JCentral that's a binary dependency, so you can compile it against others. It's not a lot of fun to custom compile C code all the time. If I could just get this ready-made from the internet, it would be nice, right? So I could just have a Gradle dependency, and it would just give me this, and I could link my C++ code against. And lastly, it would be awesome if OEMs and Google could actually provide Symbo servers. The the Microsoft ecosystem, which is very similar to the Android ecosystem, where you have, maybe you only have some Windows versions, right? But you have a ton of OEMs that write custom driver code, that adds all kinds of stuff that appears in your stack trace. On Windows, for probably 20 years, there's the concept of Symbol Server. For any stack trace that you get out of a Windows system, you can go to the Microsoft Symbol Server and you get all of the stuff. Even for your graphics card, if you have an NVIDIA driver that crashes somewhere, that's there. Unity has that. So there's a concept and a history of making this data available. So it would be great if you could get this. It would make everybody's life easier. It looks a little bit like, okay, this is a crash reporting company. Of course, they're going to have this problem. But you can see on the internet, there are lots of people in the open source community that would love to have this data available. It would unlock a whole bunch of possibilities that are currently just not there. And it would make the life of C and C++ developers much greater. And with that, if you have any questions, I'm more than happy to answer.